All right, let's talk about one of the most feared parts of the machine learning interview process, the ML system design question. You know the one, it's that big, scary, open-ended prompt that can feel totally overwhelming. But what if I told you there's a roadmap, a way to conquer it every time? Well, that's exactly what we're going to break down today.
Yeah, this quote from Alex Shu just hits the nail on the head, doesn't it? If you've ever felt your heart sink when an interviewer just casually says, "So, design YouTube," you are definitely not alone. The thing to remember is that these questions are meant to be intimidating and vague. The real goal isn't for you to have the perfect answer, it's for them to see how you think your way through a complex problem.
So, here's our game plan for this journey. First, we're going to stare down that blank whiteboard and figure out how to tame all that ambiguity. Then, I'm going to give you a simple four-step roadmap you can use for any design interview. After that, we'll dive deep into the technical toolkit, the fun stuff like data, features, training, and deployment. And finally, we'll see how to put it all together to absolutely nail your design.
Okay, that empty whiteboard. It can feel like a vast, empty space, right? But here's the secret. It's not about pulling a single right answer out of thin air. It's all about having a structured way to tackle the problem and navigate all that uncertainty.
And this is where a solid framework becomes your absolute best friend. Think of it as a repeatable process that lets you take control, guide the conversation, and really show the interviewer that you know what you're doing. And here it is, a fantastic four-step framework adapted from Alex Shu's work. Number one, and this is crucial, you have to understand the problem. Ask a ton of questions, clarify the requirements, and lock down the scope. Don't just start drawing boxes. Step two, sketch out a high-level design, a basic blueprint, and get the interviewer to nod along. Get their buy-in. Third, that's when you dive deep into the really juicy core components. And finally, step four, you wrap it all up by talking about the real-world stuff. How does it scale? What happens when things break? What trade-offs did you make? This is your map. Use it every single time.
All right, now it's time to start filling up our technical toolkit. Every great machine learning system is built on its raw materials, and that means data. But what's even more important is how we translate that raw data into a language that a machine learning model can actually understand.
And that really is the fundamental question here, isn't it? It's the art of feature engineering. A model has no idea what a cat is or what user ID 123 represents. It just sees numbers. So we have to find a way to translate those complex ideas into a numerical format, and how we do that makes all the difference in the world.
Now check out the contrast on this slide, because it's really telling. Over on the left, you've got one-hot encoding. It's simple, right? If you have 1,000 different words, you get this huge vector with 1,000 spots, where only one is a 1 and all the others are zeros. It's incredibly sparse, and it doesn't know that king and queen are related. But then look to the right. That's an embedding. See how it's a short, dense list of meaningful numbers? That's the key.
So what's the magic here? The whole point is that embeddings capture meaning. Through training, the model learns that the vector for cat should be mathematically close to the vector for animal, but really far away from the vector for car. This ability to represent these kinds of relationships is basically a superpower in modern ML. It's used for everything from words to products to people.
Okay, so we've got our features figured out. Now it's time to actually build the model. But here's a crucial thing to remember for the real world. A model isn't some project you build once and then forget about. No way. It's a living, breathing system that has to be constantly trained, evaluated, and updated.
Think about the scale of a company like Google or Meta. You can't just load petabytes of data into your computer's memory. So how do they do it? This slide shows the trick. They store the data in super efficient formats like Parquet, which arranges data by column to make it faster to read, and then they partition it, usually by date. This lets their training jobs chew through these massive data sets one manageable byte at a time.
And this is so important. The world is always changing. People's tastes change, new products come out. Your model will go stale if you let it. So you need a retraining strategy. This slide lays out a few options. Level 1 is the big one, a full retrain of the entire model. But you can also be more surgical. Levels 2 and 3 show how you might just update smaller, more personalized parts of the model much more frequently to keep them fresh. So, before you unleash a new model on millions of users, you have to know if it's actually any better than the old one, right? That's where offline metrics come in. A super common one for classification tasks is the area under the curve, or AUC. Basically, that curve plots how good your model is at finding true positives without accidentally flagging false positives. The higher the curve, the bigger the area underneath it, and the better your model is.
It's pretty clear here that the SVC model, with an AUC of 0.97, is the winner.
We've built a model, we've tested it. Now for the really hard part, making it work in real time for millions of people and making sure it doesn't fall over. This right here is where system design skills truly come into play.
So let's build a system, starting simple. This is a classic pattern for something like an ad ranking system. A user's phone makes a request. It first hits a retrieval service. Its job is to very quickly grab a whole bunch of potentially relevant ads from a massive database. Then it hands that smaller list off to the ranking service, which uses a much smarter, heavier ML model to score each one and pick the absolute best to show the user. But hold on, what if that user just looked at 3 different pairs of running shoes in the last 5 minutes? That's super valuable fresh info. So our system needs to evolve. We can add another data source, a stream of near real-time user actions that feeds directly into our retrieval service. This makes its first pass much, much smarter and more relevant.
Now what happens when it's Black Friday and traffic goes through the roof? We need to scale, and fast. In the modern world, these services are packaged up into neat little boxes called containers, which in the Kubernetes world are called pods. Then you have an orchestrator, like Kubernetes, that acts as a traffic cop. It sees the traffic jam and automatically spins up more pods to handle the load, then shuts them down when things get quiet. It makes the whole system elastic.
But with all this scale and complexity, new dangers creep in. And this is a famous, really painful story from Spotify. It turned out that the code pipeline they used for offline training transformed a feature in one way, but the live online code that served recommendations transformed that same feature in a slightly different way. This tiny, almost invisible bug went completely undetected for 4 months, quietly making the recommendations worse and worse.
This sneaky problem actually has a name. It's called training serving skew. It is one of the most common and dangerous ways that production ML systems fail. The model looks perfect in all the offline tests, but in the real world, it's getting different data than it was trained on, so it performs poorly. Just mentioning this concept in an interview and talking about how you'd prevent it, like by using a shared library for feature logic, instantly signals to the interviewer that you're thinking at a senior level.
So we have our 4-step interview framework, and we have our technical toolkit, full of concepts like embeddings and retraining. Now, let's put it all together and see what a winning design presentation actually looks like.
And this is the complete pattern in a system we all use every day, YouTube. The reason this 2-stage design is everywhere is because it's a brilliant solution to balancing speed and accuracy. Look, it's just way too slow to run a super precise, heavy-duty ML model on every single video on YouTube. So instead, a fast, lightweight candidate generation service first narrows a pool of millions of videos down to just a few hundred. Then, a much more complex ranking service can take its time to score that smaller set and pick the final recommendations. It's the exact same retrieval and ranking pattern we saw before, just at a mind-boggling scale.
So, to wrap it all up, here's your winning strategy. Always start with that 4-step framework to give your answer structure. Show that you know the core building blocks we've talked about: features, training, serving. Make sure you talk about the real-world trade-offs, things like speed versus accuracy. And most importantly, always bring your design decisions back to those product requirements you clarified right at the very beginning.
You now have a powerful framework and a solid toolkit of core ML system design concepts. The only thing left is to practice. So, what's it going to be? Are you going to start by sketching out a newsfeed, a search autocomplete system, maybe a system that predicts food delivery times? The blank whiteboard is waiting for you.